Right. Once again, good afternoon to you all. It is scheduled to have 4 lectures for this hydraulic engineering 2 module, and this is the 3rd lecture. So this is the groundwater part that we start today, and there is another one more lecture. In that lecture also, I will continue the discussion about this groundwater. Earlier, we discussed about the open channel flow and the sediment transport, right? So if you have any questions, please feel free to ask anytime you need, all right? So today I am going to discuss some introduction to the groundwater hydrology and also a set of governing equations that we can use to simulate the groundwater flow, all right? So let me start with giving you a brief introduction for the importance of the groundwater aquifer and the groundwater flow simulation, right? So the hydrological processes, and you know that they are in a hydrological cycle. So that the processes like the rainfall, evapotranspiration, then the infiltration, they all are in a hydrological cycle. Therefore, it is very important to have a balance between each of these hydrological processes. If one hydrological process is disrupted, then it can have serious consequences for the other hydrological processes, right? So that is why it is important to have a balance for this groundwater aquifers as well. When we talk about the balance of the groundwater aquifer, groundwater recharge and the groundwater extraction are the main processes that control the water balance of this groundwater aquifer. For example, for the irrigation purposes, domestic purposes, we extract groundwater from the groundwater aquifers. On the other hand, the natural recharge and the artificial recharge govern the water that we add into the groundwater aquifer. It can be a natural recharge from rainwater or the rivers, wetlands, right? So these ecosystems also recharge the groundwater aquifers. So that again, there should be a balance between them. Changes like the climate change, urbanization can have serious impact for the groundwater aquifer. Ultimately, it can change or it can disrupt the entire water balance. That is why it is important us to study about the groundwater aquifers and how we can model the groundwater aquifers, groundwater flow, right? So these are the things we are going to discuss in this module today and the next class, right? So the hydrological processes, as I said, they are in a cycle. So if you consider the precipitation over the land surface is, let's say, 100%. Out of that, you know, the evapotranspiration is a very significant component. So that the evaporation alone out of this 100 accounts nearly 60%. When you go to the arid countries, the potential evaporation can be as high as 80%. So it changes with the climate zone. But in general, you can say the evaporation alone is about 60%. Then we have the surface runoff, right? So if you compare this precipitation with the groundwater flow, it is only about 1%, right? So probably you undermine the importance of groundwater flow by looking at these numbers. But you need to understand why this is 1%. The reason is, if you compare it with this 38% of the surface runoff, the reason why it is so small is that the groundwater flow, when compared with the surface water flow, is very, very small. Groundwater velocity is very small. That is why, in fact, it is acting as a resource, groundwater resource, right? so that the groundwater recharge the aquifer today can be used maybe after 10 years or even after 100 years. That is why it is acting as a resource. So this is just you to understand how much water that we have in earth, right? Then how much water actually we can consume. Then what is the percentage of the water that we see on the ground surface, right? So you know there are 5 main reservoirs. What are they? They are the oceans, ice caps, groundwater, then the lakes and the river. They are the surface water bodies, and the atmosphere. Atmosphere govern the rainfall pattern, right? Atmosphere moisture amount. But when it comes to the groundwater, probably you undermine it because you don't see it, right? But if you consider the availability of the fresh water and the percentage of that from the groundwater, that is quite significant. Now, if you consider the all water that we have in the entire planet, then here the seawater or the saline water is accounted about 97%. Out of that, now, if you consider the freshwater availability, it is only like 3%. Now, the question is, can we use all these 3%? No. Again, the nearly 68% of that 3% is ice and glacier, where we can see it in Antarctica, Arctica, right? Bolivian glacier, then the Alps region. This is where these ice caps and the glacier are located. So that, again, this water has very high retention time. For example, the retention time of the glacier is about 10,000 years or more than that, right? Again, we don't use this water very often, right? Then the groundwater, nearly 30%. So now you understand the magnitude of the groundwater resource. Others is only like 0.9%. So these others include the surface water body, which is about 0.3%. Now I would like you to compare these two. See, the surface water is 0.3 and the groundwater 30%. That is why, comparatively, this is a large resource. In fact, this groundwater resource is considered as the foundation of all the ecosystems. Like, let's say, if you are talking about a building, the foundation is the most important part, right? No matter how beautiful it is from the outside, if the foundation is weak, then the building can collapse at any time, right? So similarly, this groundwater aquifer is considered as the foundation of the entire environment or the surface ecosystems, right? It is that important. Now, the climate change, as I said, climate change and the urbanization can have serious impact for the balance of the groundwater resource. Now, for example, in many arid countries, they depend on groundwater resource to meet their demand. For example, in Oman, nearly 75% of the water demand is coming from the groundwater, right? So even in Sri Lanka, if you go to the Jaffna, Kilinochchi, then Anuradhapura, Polonnaruwa, Hambantota, right? So we depend on the groundwater a lot to meet the demand. It can be the domestic water demand, or it can be the agricultural or the industrial water demand, right? So this figure here shows the global water stress in 1995. And you can see in the future, like not so far from today, by 2025, this is expected to expand the global water stress like this, right? So the Sri Lanka is one of them. That is why it is important us to understand the balance of the groundwater resource and how it can be disrupted and how we can effectively or sustainably use this water resource. Right. So far, do you have any questions?
No, sir.
Right. Okay. Thank you. So now, why it is important? This is according to some literature. It is a priceless value of fresh groundwater, not only as a source for water supply, but also as an important factor governing the productivity of the arable lands and as a vital element in the natural environment. Now, there are so many case studies that they have found because of the sea level rise and seawater intrusion, the coastal aquifers now have become unproductive. Why it is? Because from the freshwater side or from the landslide, if you are pumping too much water out, then what happens? The seawater start intruding into the groundwater aquifers. Therefore, what happened? The salinity level of these groundwater aquifers becoming higher. Now you know that we have a very interesting case study in Sri Lanka, the Nilwala salinity barrier, right? So these are the effects. Now, because of this, the agricultural land productivity gradually decreases, right? So it is one of the serious consequences of disrupting the balance of the groundwater aquifer. Then growing awareness of the problems associated with overdrawn aquifers and of the unwanted side effect of the groundwater exploitation. If you are pumping too much water out, then what happens? What are the consequences? Land subsidence. Can anyone tell me where the land subsidence has become a serious issue? Any case studies that you know? It is used to be a serious issue in countries like USA because during the industrialization time, they pump so much groundwater out, right? So that because of that, the land subsidence was a serious issue. After that, like agencies like Environmental Protection Agency, they started regulating the groundwater pumping and now it has become under control. But still, countries like Thailand, then Indonesia, they have serious issue with the groundwater pumping and the land subsidence. Then well drying up, saltwater intrusion, seawater intrusion, reduction in crop yield, and decrease in surface water discharge. They are the serious issue of this groundwater imbalance. Now, problem of groundwater pollution and possible changes in ecosystems due to changes in groundwater level and flow. Groundwater is less polluted compared to the surface water. That is why if you go to the rural areas, right, even in urban areas like Kalani River Basin, for example, still we depend on the groundwater wells, right? So not only for the domestic water supply, but also for the industrial and agricultural water demand, we use the groundwater. Why it is? It is considered as a less polluted compared to the surface water. But higher cost and longer durations for recovery are required. If it is polluted, it is not easy to remediate or recover. That is the danger there. Further, it is a hidden danger as a groundwater pollution is difficult to be identified. It is very difficult. If the surface water is polluted, you can see it, right? But if the groundwater is polluted, it is very difficult to identify. Unless you do a couple of tests and identify it, you are not going to see it until it has a serious consequence. Therefore, it is very important us to maintain these groundwater aquifers and should not be polluted, right? So hopefully next class I will be able to discuss about some source of this pollution and how the groundwater aquifers once polluted can be remediated, right? So need for preservation and protection of groundwater and its assessment and sustainable development as a natural resource. For that, we need the policies, regulations, and the strategies. Can someone tell me what is the authority in Sri Lanka responsible for the groundwater? Anyone? What is the authority in Sri Lanka responsible for the groundwater? Policies, regulations, strategies? What do you think? Is it the Central Environmental Authority or the Water Supply and Drainage Board or anything else? Anyone? It is the Water Resource Board, right? In Sri Lanka, if you want to use groundwater, let's say for a factory, right? Then you have to get the permission from the Water Resource Board, right? So that is the authority in Sri Lanka responsible for the groundwater regulations, all right? Yes. Now, I will go through some basic definitions that we need. Then I will talk about some groundwater properties that we need to talk about when we are simulating the groundwater flow, right? Then only I can talk about the groundwater flow equations. All right. So the first, groundwater aquifer. What is this aquifer? And are there any other different kinds? Right? So the aquifer is a geological unit that can store and transmit water. The key word here is the store and transmit. These are the two important keywords. It should be able to, this geological formation that we discuss, should be able to store water. A significant amount of water should be able to store. Not only store, it should be able to transmit. This water should be able to extract or pump out or should be able to flow. In that case, we call it is an aquifer. Right? So what is the difference of that to the other? Like, for example, the aquifuge. What it is? Absolutely impermeable layer. Absolutely impermeable layer. Can you give me an example? Like granite, for example. The bedrock, if it is formed by granite, for example, then you know that the granite are absolutely impermeable layers, right? So that is considered as an aquifuge. Or very often, we call it is an impermeable layer. Then the aquiclude, what it is? A low permeability unit that forms upper or lower boundary. It has a minimum storage and cannot transmit. So it is not as impermeable as the aquifuge. It has some storage, but the issue is that it cannot transmit, right? That is an aquiclude. Then this is very oftenly discussed in groundwater hydrology, that is called the aquitard. So what it is it's a low permeability unit that can store and slowly transmit water. Can anyone give me an example? What kind of geological formation it is? Aquitard. You can hear me, right? Sajiv, can you give me an example for this? Aquitard. It can store water, but it cannot transmit. What kind of aquifer it could be? Oh, sorry, aquitard it could be. Lakmali, what do you think? You can hear me, right? At least can someone tell me if you can hear me or not?
Yes, sir.
Right, very good. Then can you give me an answer for this aquitard? What kind of geological formation it could
The clay layer.
Yeah, very good. That is a clay layer. Now, later on, I will discuss about the porosity and the hydraulic conductivity, these terminologies. But in general, you know that the porosity of the clay is very high, so that it can store a large amount of water. But it is not considered as an aquifer. That is why I said these two are the key words here. Aquifer, it should be able to store very large amount of water. Also should be able to transmit. So if you consider the clay, clay can store large amount of water, but it cannot transmit. Permeability and the hydraulic conductivity of the clay is very, very small. Therefore, you cannot extract water. You cannot pump water out from clay. That is why it is considered as an aquitard. All right, very common in Sri Lanka, also in many other places, right? Okay, so now about the type of the aquifer. This is very important. The reason is that the governing equation that we use to simulate the groundwater flow depend on the type of the aquifer, right? Think about this, not only the governing equation, but also the practicality of these groundwater studies. Now, if you ask your grandfather or grandmother about drilling a well, they will tell you drill a well to the deep so that you can take more water. So why it is? If you drill it to a shallow depth, why you can't extract water in large quantities, right? Or during the dry season, what will happen to the well, right? That is depend on whether you are drilling this well to the confined aquifer or an unconfined aquifer, right? So what is this confined aquifer? It is an aquifer bounded above and below both by impermeable beds or by beds of distinctly lower permeability than that of the aquifer itself. So that kind of aquifer is called the confined aquifer, right? So this is an example. This is a confined aquifer. Now you can see it is bounded by two impermeable layers. So that kind of aquifer is a pressurized aquifer. So that if you drill a well to this aquifer, now you can see this well can give you the water throughout the year, right? In fact, if the hydraulic head of this well in this aquifer is larger than the hydraulic head gradient that you see somewhere here, then it will be acting as a spring, artesian well. All the time the water will come out, right? So this is a pressurized aquifer. Now, what is the difference of this one to the well that you drill into an unconfined aquifer? This is an unconfined aquifer. What is the difference here? Unconfined aquifer is bounded by an impermeable layer only at the bottom. But on the top, what do you see is the ground surface and unsaturated layer. That kind of aquifer it is called unconfined aquifer. Now, what will happen if you drill a well here this water level can have or can fluctuate seasonally, or if you start pumping too much water out, then the groundwater level can deplete within a short period of time. That is why it is important, especially for the water schemes. Now, if you are working in the National Water Supply and Drainage Board, right? So you will be asked to design a pumping well scheme, right? There, it is important you to drill or do a pumping test and make sure that you drill the well into the confined aquifer, right? That is the difference. Now also, you have to be careful. Sometimes there is another one called the purge aquifers. What it is, they are very localized aquifers, bounded by this kind of a very small clay layer or impermeable layer, so that very small amount of water is accumulated there. Therefore, if you drill a well for this, for a short period of time, it may satisfy your requirement. But you need to understand within a short period of time, it will dry up, right? So you have to be very careful about these kind of purge aquifers. Right. Now, piezometric level. Probably you remember when we discuss about the pipe flow, open channel flow, there are three head terms we discuss. What are they? Pressure head, velocity head, and the elevation head, he said. But when we talk about the groundwater flow, as I told you earlier, the velocity of the groundwater flow is quite small. Therefore, this can be considered as, or we can neglect it. Therefore, the piezometric level for the groundwater flow is the pressure head plus the elevation head. So that is what this line here indicates. Why this one has a negative gradient? Why it is decreasing like this? Why it is not increasing? Anyone? Why this line has a negative gradient? It is because of the head loss. Compare it with the open channel flow or the pipe flow. When the water flow through a pipe, because of the friction effect, there is a head loss. So similarly, when the water go through the porous medium, there is a head loss. That is why this piezometric head level decreases in the direction of the water flow, right? Okay. So again, this is the same discussion about the confined, unconfined aquifers, then the purge aquifer, piezometric head, right? Okay. And now in Sri Lanka, we have different geological formations. Like for example, if you go to the Jaffna, Kilinochchi, Mana area, the area is dominated by the karstic aquifer that we call the lime and dolomite aquifers, right? Therefore, there the porosity is governed by the cracks and some holes generated by the weather or the chemical reactions, right? So this is how the water flow through the aquifer. But if you come to the southern belt here, the formation is called the lateritic. In Sinhala, we call the kabok, right? So the aquifer is dominated by the lateritic formations, right? Then if you go to the river basins, how many river basins we have in Sri Lanka? Major river basins? Anyone familiar with the irrigation department? If you are working in the irrigation department, or if you have been to the training in an irrigation department, how many river basins, major river basins we have in Sri Lanka? Altogether, there are 103 major river basins, right? So along the river basins, along the river, we can see the alluvial aquifers. Then sandy aquifers are dominated in many places. Like that, geological formations in different areas are different, right? Okay. Now, hydraulic conductivity and permeability. Hydraulic conductivity and the permeability, they are the soil properties and indicate the ability of the water movement through the aquifer. What I mean is how fast the water can flow through the aquifer. That relate with the hydraulic conductivity and the permeability. So what is the difference between this hydraulic conductivity and the permeability? Both of them are the indication of the ability of the water movement through the aquifer. But what is the difference? Permeability entirely depend on the properties of the soil. Permeability depend on entirely the properties of the soil. But the hydraulic conductivity depend on both the soil properties and the liquid properties. If you are talking about the groundwater flow, then the properties of the groundwater. What kind of properties? What are the properties of water that you learn? You don't know any properties of water?
Viscosity is
right. Very good. Viscosity, density, right? They are the properties of water. So the hydraulic conductivity depend on both soil properties and water properties. That is the major difference. Other than that, both of them indicate the ability of the water movement through the aquifer layers, right? So you need to have some idea about these values. For example, if it is an alluvial aquifer, we can say the hydraulic conductivity is approximately like 10 meter per day. It can change from like 1 to 100, right? But in general, you can say it is in a range of like 10 meter per day. But if you consider the clay, now you can see it is like 10,000 times less, right? So that is why clay is not considered as an aquifer formation. It is considered as an aquiclude or an aquitard, right? So better to have some idea about the magnitude of these different geological formations, right? Now, in different fields, we are not the only one, like the hydrologist or the civil engineers are not the only one use the aquifers. Like, for example, if you consider the petroleum industry, they use different definition, different terminologies. So to indicate the hydraulic conductivity, we normally use meter per second or meter per day, like that. But in petroleum industry, they use a unit called the Darcy, right? I'm not going to talk about them, but in hydrology field, we use it as length over time. So this can be meter per day. Very commonly we use meter per day, right? So this variation here shows you how the hydraulic conductivity change for different formations. Now you can see the gravel has like the highest hydraulic conductivity. And also the porosity of the gravel is higher. Not as high as the porosity of the clay, but the porosity of the gravel is comparatively higher than the most of other geological formations. Therefore, it is considered as a good aquifer, right? But you see the silt, then the clay, hydraulic conductivity can be like thousands or 100,000 times less than some other geological formations. Right. So what are the factors affecting for the ability to store water and ability to transmit water. In other words, what are the factors affect for the porosity and the hydraulic conductivity? Now, in general, I want to emphasize the term in general, okay, not always. In general, when the particle size is higher, the porosity become higher. What is the definition of the porosity? That is the volume of the void over the total volume of the aquifer. Right? So if you consider an aquifer formation like this, these are the voids. So this is where the water is stored. Right? So that the porosity is an indication of how much water we can store there. Now, when the particle size becoming higher, the coarse particles, in that case, a large amount of water can be stored. For example, gravel. Gravel can store large amount of water. On the other hand, when the particle size becoming smaller, the porosity decrease. But this contradicts with the case of the clay. If you compare the gravel and clay, gravel has a smaller porosity, but the clay has an higher porosity. I will explain why later. So that is why I said this is in general. Then the packing, whether it is loosely packed like this or whether it is tightly packed like this. In that case, if it is loosely packed, you can see the porosity is higher. Then the matrix, the packing can be like this or it can be like this, right? So depending on how it is packed, then the porosity can vary, right? So these are the sorry, I was disconnected. Can you hear me?
Yes, sir.
Yeah, very good. Unfortunately, I have a very bad internet connection at my home these days. So in a case, if I was disconnected, please stay for a while. Somehow I will find a way to connect back. All right, so I will start it again. Right, so we were discussing about the porosity, right? So the, now the how this porosity difference can be explained when it comes to the case of the clay and the gravel. Now you see the size of the gravel particles. Normally we call, if it is more than like 2 millimeter, we call it is gravel particle size, right? The sand is within like 1 millimeter size. Now you can see the silt much smaller than this. Even you cannot see it here. But silt particles are larger than the clay particles. So the clay is even invisible at this scale, right? But why the porosity is higher? The reason is the clay, the particle size is uniform, relatively small, and relatively uniform, right? In that case, it can have or it can store a very large amount of water between the particles. That is why the porosity is quite high. But what is the reason? It is considered as an aquitard. Aquitard means what? It can store water. So the porosity is higher so that the clay can store large amount of water. But why it is considered as an aquitard? The reason is it cannot transmit water. What is the reason? Now you understand, when the particle size is smaller, we are talking about very small size, but the surface area, when you consider the entire formation, the surface area of the particles can be quite large. Yes, we are talking about very small particles, but the surface area of these particles, when you consider them together, can be quite high. Therefore, the attraction between the water particles and the clay particles is very high. That is why this water does not flow very easily, right? So that is the reason the hydraulic conductivity is quite small, but the porosity is quite high. That is why it is considered as an aquitard formation, right? So I hope it is clear. Now, the shape of the particle. If they are like round shape, then you can understand that the space between them can be quite high, so that the porosity is quite larger. But if they are like flat or angular shape, then in between the particles, other small particles can be filled, so that the porosity decreases. So that is about the shape of the particles. So I have given you an assignment or a tutorial. I'm not sure how it will be given to you, but the first question of that assignment, you will see I have asked you to develop or find out the porosity when the particle size is the same and exactly the round shape. So you will find out there, in that case, the porosity that you calculate become independent of the size of the particle. If they are in round shape and the same size, then the porosity become independent of the particle size. But in general, you don't find exactly the same particle size and round shape, right? Because of that, the shape of the particle also affect for the porosity. Then the sorting, whether it is well sorted or poorly sorted case. Well sorted mean approximately the same size, so that there are a lot of space between them. Poorly sorted mean the case like this. Think about this. You have a sample, gravel sample, and also silt or sand sample. If you get them separately, hydraulic conductivity of the gravel is higher than the hydraulic conductivity of the silt. But if you mix them together, what will happen? The silt or the sand particle will move into the gravel particle and the porosity will decrease. Right? The reason is in between the voids, these small particles will be filled, so that the amount of the water that formation can store decreases. So this is called the poorly sorted formation. Right? Yes. Now, this is a good example you to understand the how the water transmit through different formations. For example, if you consider like 1 meter long sediment column or the sand gravel column, so how the water move through them. Now think about this. We have like 1/4 of space here. If you put water here, this water will drain out within a very short period of time, like 2 minutes for the gravel. But for the sand, it will take more than 2 hours to drain out. If you consider the silt, this is after 200 days. You can see only a very small amount has drained out. Clay, this is after 200 years. So the water movement is quite small. But yes, it can store very large amount of water. Right? So this is an indication, or this is a good figure you to understand the hydraulic conductivity, how it change for different formations. Now, the particle size and the capillary effect. Can someone tell me why or how the capillary force is generated? You remember the capillary effect, right? Capillary force is generated because of the attraction between the unlike molecules. For example, if you put water into a very small tube like this, then what will happen? The water will, probably you remember you did an experiment when you were in the school, right? There is this water and you put a beaker like this, not a beaker, a small tube. So what will happen? The water start rising more than the water level in this beaker, right? So the reason is the capillary effect. How it is happen? It is happen because of the attraction between the unlike molecule. In this case, what are the unlike molecules? Glass and water molecules. So that attraction is higher than the attraction between the water and the water molecule. That is why it is going up. That is called the capillary effect, right? So if the particle size is smaller, then the capillary effect is greater. For example, like clay, the capillary rise can be more than 1 meter. But when it comes to like sand or the gravel, capillary rise is smaller compared to the clay. So that it is mainly affected by the particle size. When the particle size becoming smaller, capillary rise is higher, right? Yeah. So now, what are the different zones that we can see in an unconfined aquifer, right? So in an unconfined aquifer, if you drill a well to the unconfined aquifer, the first thing you want to see is where is the water table, right? So that level is called the water table. This is the water table, right? Then above this water table, we have the capillary layer. Capillary layer. So as I explained you earlier, this capillary rise will depend on the size of the particles. If it is clay, capillary rise is higher. But if it is like gravel, sand, the capillary rise can be smaller. Anything above that, we call it is the unsaturated layer. Unsaturated. Why it is called the unsaturated? Because the voids here is not completely filled with water. There are still some spaces that you can use to fill with water. That is why it is called the unsaturated layer, right? Now the area below this water table, it is called the saturated layer. So this saturated layer is completely filled with water. All right, is it clear? I'm very sorry, I think I was disconnected again. So let me share the presentation again. Yes, you can hear me, right? Can someone please speak?
Yes, sir.
Right, okay, thank you. Yeah, okay. Right, so we were talking about the unsaturated zone and the saturated zone and the capillary effect, right? So the area below the water table is called the saturated zone. Right. So how does the groundwater move? What we expect water to move like the pipe flow, right? That is normally our idea about the groundwater flow. We think that the entire cross section is contributing for the groundwater flow. But actually what happened is that the groundwater, if the water need to flow through the aquifer, it has to have the interconnected voids. Having the porosity, high porosity, does not help alone. These voids that we have in the aquifer should be interconnected. Otherwise, the water cannot flow through the aquifer. You need to remember a large part of the aquifer consists of the soil particles. And if the voids are not interconnected, then the water movement disturbed, right? But when we write the governing equation, we consider that the water movement is like this into a particular direction. But in actual case, it is not like that. Water flow through the interconnected voids, right? So that is the groundwater movement. Therefore, you need to very clearly understand what is the area actually contribute for the groundwater movement. If you consider the pipe flow, the entire cross section contribute for the water flow. If it is an open channel flow, again, entire cross section contribute for the water flow. But if it is the groundwater flow, only the interconnected voids contribute for the groundwater flow. But when you are writing the governing equation, you are writing it like this. So how do we account this effect, right? So this will be discussed later. Now, groundwater wells. You understand a well, it is a deep hole, generally cylindrical, that is dug in drill into the ground to penetrate an aquifer within the saturated zone, right? So that if you drill it to an unconfined aquifer, then unconfined aquifers are subjected to the seasonal variations. Therefore, during the dry period, the well can dry up or the water level can significantly decrease. But in rainy season, the water level can again increase, right? For example, if you go to the Jaffna or the Kilinochchi area, especially like in the Kilinochchi area, you know that it is a karst aquifer. Therefore, the water level in Irnamadu reservoir directly connect with the aquifer, groundwater aquifer. So the water level is sensitive to the water level in the Irnamadu reservoir, like that. So the water levels in aquifers, in unconfined aquifers, can be connected to the surface water body, therefore sensitive to the water level variations in surface water bodies. Right. Something very important, it is the cone of depression, what it is. Now, if you are pumping water out from the groundwater aquifers, initially this can be the water level before you start pumping. But when you start pumping water out, what happens? The water level near to the pumping well decreases rapidly. But that change decreases as you go away from the well. So that actually, when you see from the top, what you see is a formation like a cone. That is why it is called the cone of depression. Cone of depression, right? So this drawdown is defined as the water level difference between the original groundwater table or the original piezometric level and the current one, since you start pumping water out. So that this is the drawdown, right? So the drawdown decreases as you go away from the pumping well, right? So the cone of depression, it is a depression of the water table formed around the well when water is pumped out. It is shaped like an inverted cone. That is why it is called the cone of depression. Right. So when you drill a well, this is very important. Remember, when you drill a well, you disturb the aquifer formation. Therefore, the pollutants, surface water pollutants, can easily penetrate to the groundwater aquifer. Groundwater is considered as a less polluted water source. Why it is? Because the pollutants filtered when the water infiltrate through the soil layers, through the unsaturated layer. But if you drill a well, then you are making a connection from the surface, ground surface, to the groundwater aquifer, so that the surface water pollutants can easily penetrate or enter into the groundwater aquifers. Therefore, when you drill a well, it is very important you to seal it like this. So what I am showing you is this one. This is actually a project that we did in Muscat in Oman. So there in Muscat airport, we drill a series of well to control the water level rise in the airport. Right. So this is one of the example. So you need to seal it from the top. Right. Then there is one more important thing is called the screen of the well. So well screen. Actually, this is what you see in a pipe. Not the entire pipe is contributing for the water flow. Water can enter into the well only through the screen. Right? So this screen height is very important when you are talking about the pumping test or the groundwater movement when the water is pumped out. The reason is that water enter to the well only through the screens. And also you need to understand that there is a head loss when the water go through this kind of very small screens, right? So that they all need to be considered. Now slowly we are moving towards the governing equations. But before we start governing equations, we need to discuss the definitions of the aquifer properties, right? So the porosity, you understand. Porosity is defined as the ratio between the volume of the voids and the volume of the aquifer. So the more voids that you have, the higher the porosity. That you understand, right? Then the permeability. As I said, the permeability, it is the ability of an earth material to transmit water. So the permeability depends only on the properties of the soil. But if you consider the hydraulic conductivity, normally for the hydraulic conductivity, we use the capital K. Notation is capital K. Simple K is used for the permeability, right? So the hydraulic conductivity depend on the permeability and the properties of the water or properties of the liquid. So what are the properties? Rho is the density, mu is the dynamic viscosity, right? Then the units. Hydraulic conductivity has the unit. It can be like millimeters per hour, meter per second, or commonly we use the meter per day, right? Meter per day. So you need to remember them, the difference between the hydraulic conductivity and the permeability. Right. Now, when we do the pumping test and when we see the governing equation of the groundwater flow, there is a very common important parameter that is called the transmissivity. What is this transmissivity? That is the rate of the flow through an aquifer of unit width. The aquifer should have a unit width. Then extending the full saturated height under the unit hydraulic gradient. That is defined as the transmissivity. In other words, there is a very simple relation between the transmissivity and the hydraulic conductivity. What it is? Transmissivity, that is the capital T, is equal to the hydraulic conductivity, which is K, multiplied by the saturated thickness of the aquifer. If it is a confined aquifer, that is the thickness of the aquifer itself. But if it is an unconfined aquifer, that is the height from the impermeable layer to the water table, right? For the unconfined aquifer. Saturated thickness for the unconfined aquifer is like this. Let's say this is the impermeable layer. And this is the water table. In that case, this is the saturated thickness, right? So transmissivity, it is considered as the hydraulic conductivity multiplied by the saturated thickness, right? Yeah. Now, hydraulic conductivity, permeability, and the transmissivity, they all indicate the ability of the water movement through the aquifer. We also need the storage parameters. How much water can store and then transmit. So when we talk about the groundwater flow, the transmission part is handled by the parameters like the transmissivity, hydraulic conductivity, permeability. But how much water can store? Then again, there are a set of parameters, right? The first one is called the storage coefficient. Storage coefficient. In other words, it is also known as the storativity. So what it is, what is the definition? A very simple definition. That is the volume of water that an aquifer releases from or take into storage. How the water release from the aquifer? Water release when you pump water out. How the water take into the storage? It can be the natural recharge or it even can be the artificial recharge. In countries like Oman, Saudi Arabia, UAE, they inject water into the groundwater aquifer. That is called the artificial groundwater recharge. Why they do it? Because later they can use this water. During the rainfall time, they store water and artificially recharge the groundwater aquifer so that later they can use this water. Right? So that is the artificial groundwater recharge. Right? So now, what is this storativity? That is the volume of water that an aquifer release for the pumping or take into account for the natural recharge or artificial recharge per unit surface area. Now, if you consider the aquifer, we are talking about a unit surface area like this. Let's say it is 1 meter by 1 meter area. Then, if you reduce the head normal to that surface, hydraulic head normal to this surface, if you reduce it by 1 unit, then what is the amount of the water that you can pump out? That is called the storativity or the storage coefficient. Now you understand we are talking about a water volume that we can pump out, water volume per unit surface area of the aquifer. And you are reducing the hydraulic head by 1 unit. So now what is the unit? Volume divided by the area divided by the length. This becomes unitless or dimensionless. So the storativity is a parameter which has no unit, dimensionless parameter. Right? Again, you need to have some idea about the magnitude of this. If it is an unconfined aquifer, storativity or the storage coefficient is relatively higher. But unconfined aquifer, it is very, very small. Now, as I told you, there is a very simple relationship between the transmissivity and the hydraulic conductivity. Similarly, there is a very simple relation between the storage coefficient or the storativity and a parameter called the specific storage. What is that relation? Storativity, it is equal to the specific storage multiplied by again the saturated thickness. So how this specific storage is defined? That is the volume of water that an aquifer release or from the storage or take into account per unit volume, per unit head change. What is the difference here? Here we are talking about a unit volume, but here we are talking about a unit surface area. That is the difference. We are talking about 1 unit of aquifer. In this unit, if you reduce the hydraulic head by 1 meter, then what is the amount of the water that you can pump out? Right? Now we are talking about the volume of water that you can pump out per unit aquifer by reducing the hydraulic head by 1 meter. Now you can understand the unit of this one become like per meter. Right? Then per meter multiplied by meter, that is the saturated thickness, become the storativity, which is unitless. That is the relation. So it is very important you to understand the relation between these variables, aquifer properties. All right. Do you have any questions so far? Any questions so far? Nalinta, any question? Can someone please speak so that I can continue? We have very limited time. Do you understand or do you have any questions? No questions?
Yes, I understand.
Yeah, you understand everything. Very good. Right. Now, couple of more definitions. The specific yield. Specific yield is the volume of water expressed as a percentage of the total volume of water, volume of the saturated aquifer that will drain by the gravity. This is a very important definition. Now think about it like this. If you have a wet cloth, like a wet towel, if you put it into a water and if you took it out, then what will happen? Water start draining out under the gravity. So basically, this specific yield is the volume of water that drain by gravity when the water table drops due to pumping or drainage. Right? That is known as the specific yield. So it is an indication of how much water is available for the use. Right? So when the water table drop, what happens? Water start draining down. Therefore, that is called also known as the drainable porosity. Theoretically, this drainable porosity should be in between 0 to 1, but it will never reach 1. In general, this specific yield is changing like this. When it come to clay, it is very, very small. But for example, like sand, gravel, it can be relatively higher. That is specific yield. Right? Then the specific retention, what it is the percentage volume of water that will not drain by gravity. No matter, even if you put the cloth in your washing machine, you cannot drain all water out, right? So that is why you put it out, right? So the wet cloth can get dry. So how it happen? No matter how or what is the level of saturation of the aquifer, still a small amount of water will be retained in the porous medium. This water will not be drained under the gravity. That is called the specific retention. What is the reason this water does not drain under the gravity? It is because of the attraction or the suction head between the soil and the water particles. So this suction head is higher for the clay, but for the gravel, it is very small. But still, you cannot drain out 100% of water. A small amount of water will retain by the soil particles. Therefore, the porosity theoretically should be equal to the specific yield. That is the amount of the water that you can drain out and the specific retention in saturated aquifer. When it is fully saturated, that the porosity will be equal to the specific yield plus the specific retention. Right? But you learn the area below the water table is fully saturated, but the area above the water table is partially saturated. That is, we call the unsaturated layer. So the soil moisture content indicate how much water we have in that unsaturated or saturated layer. If it is a saturated layer, soil moisture is 100%. Soil moisture content is 100%. Entire water volume, void volume is filled with water. But in unsaturated layer, that is defined as the available volume of water divided by the total volume of the aquifer. If you take 1 unit volume, how much water we have there, that is called the soil moisture content. It equal to the porosity when the soil is saturated or when it is below the groundwater table. Then the soil moisture content equal to the porosity. Right. Now, we start the groundwater flow equation. The most famous equation is the Darcy equation, right? Henry Darcy developed this equation in 1856, right? So what it say, the velocity, Darcy velocity through the porous medium, if you have a soil column like this, then the velocity through this we call the Darcy velocity. That is directly proportional. Darcy found that it is directly proportional to the head difference between them. That is H1 minus H2 in this case. This is the total head at this point. And this is the total head. Sorry, this one is the total head at this point. So the head difference is H1 minus H2 divided by the L. L is the length between these 2 points. In other words, this is called the hydraulic gradient. Hydraulic gradient. So the Darcy velocity is directly proportional to the hydraulic gradient. That is what Darcy found. Right? Simple, but very useful equation. And he also found that this Darcy velocity, this proportionality we can remove by introducing a coefficient that is called the hydraulic conductivity. So actually the Darcy velocity, it is equal to the hydraulic conductivity multiplied by the dH over dL. That is the hydraulic gradient. Now, as I told you earlier, when the water flow through the aquifer, we have a negative gradient like this. Why it is? Because of the head loss. Therefore, the water flow from the higher head to the lower head. Therefore, it has a negative gradient like this. So, to remove that negative gradient, we introduce a negative sign here. Negative sign. Right? So, the Darcy velocity, we can write it like this. Darcy velocity, that is equal to the hydraulic conductivity multiplied by the hydraulic gradient. Now, you need to understand the difference between the actual velocity and the Darcy velocity. As I told you earlier, if you consider a soil sample like this, not entire area contribute for the water flow. Only the void spaces or the interconnected voids contribute for the water flow. Therefore, actual area and the area of the soil sample is different. Therefore, in fact, this area of the void is smaller than the actual area. Therefore, the actual velocity is larger than the Darcy velocity. Actual velocity is larger than the Darcy velocity. So the relation between them is that the actual velocity is equal to the Darcy velocity divided by the porosity. Porosity is less than 1, right? Therefore, the actual velocity is larger than the Darcy velocity. Okay, so I hope it is clear. The difference between the actual velocity and the Darcy velocity. Now, probably you remember when we talk about the pipe flow, the friction factor, for example, that you calculate depend on the type of the flow. It can be the laminar flow or the turbulent flow. So how do we define it? We define the laminar flow or the turbulent flow depend on the water velocity. In other words, we use the Reynolds number. So this Darcy velocity also depend on the Reynolds number. And Darcy velocity can be applied only if the Reynolds number is less than 1. That is how it is applicable. But in general, if the Reynolds number is less than 10, the error that it introduces will be smaller. It is not correct, but the error is smaller. So you can use it up to 10 according to the literature. But in general, we accept that if the Reynolds number is less than 1, then the Darcy law produces accurate result. Okay, so you need to remember the Darcy law to be applied, the Reynolds number should be less than 1. Right, now we come to the governing equation of the groundwater flow. Can anyone tell me what this is? What equation is it? This is the continuity equation. Probably you remember pipe flow, open channel flow, we discussed about the continuity equation, right? How the continuity equation was developed? It was developed by by using the Reynolds transport theorem. In Reynolds transport theorem, you have two parameters that is called the extensive property and the intensive property. So in Reynolds transport theorem, if you consider the mass as the extensive property and B is equal to 1, in that case, you develop the continuity equation, right? So continuity equation, then there are two parts in this continuity equation. What is this one? This is known as the mass flow through the control surface. Net mass flow rate through the control surface. So this CS stands for the control surface. A surface like this, if you consider 1 unit volume of the aquifer, these are the control surfaces. So how many surfaces we have? Altogether, there are 6 surfaces. So the flow rate, mass flow rate through these control surfaces and the accumulation of that is given from this expression here. What is this one? Rho multiplied by volume, that is the density. Sorry, density multiplied by the volume, that is the mass. Time rate of change in the mass inside the control volume, that is given by this expression here. In other words, if you have this volume, time rate of change in the water mass inside this control volume is given by this expression. So what it says is that net mass flow rate through the control surfaces is equal to the time rate of change in the mass inside the control volume. If it is very difficult you to understand, try to compare it with a simple case. Think about this control volume as your purse that you carry money, right? So the amount of the money that you have in your pocket depend on how much money you receive, maybe your salary, or maybe from your parents, and how much money you expend, right? Then in the end of the day, how much money will retain or remain in your purse will depend on how much you have received and how much you have expended. It is that simple. So this equation is very, very simple. So try to think about it with some practical examples. Now, we will take, what we are trying to do is to develop a three-dimensional equation for the groundwater flow, because groundwater flow is not unidirectional or two-dimensional. It is three-dimensional, right? So we need to develop an equation for the three-dimensional groundwater flow, right? So we will take part by part of this equation. Now, if you take the first part, that is the control volume, this one, time rate of change in the mass inside the control volume. So this one can be changed because of several reasons. First one is the mass rate of water produced by an expansion of the water under change in the density. Think about this groundwater flow. Above the groundwater table, there is a large mass of soil, right? There is a large mass of soil. When we talk about the pipe flow, we consider the water is an incompressible fluid. It cannot be compressed or the density is constant. But you understand, when we talk about the groundwater flow above the groundwater aquifer, there is a large mass of soil. Because of that, this water is compressed. Now, if you pump this water out, this compressibility can change, right? The compressibility can change. Because of that, the density also can change. When the density change, then the mass rate of the water can change. So that is one way of changing the mass inside the control volume. Second is the mass rate of water produced by the compaction of the porous medium due to change in the porosity. In the aquifer, this water is holding the pressure coming from the soil layers, right? So this water is, in fact, the bulk modulus of elasticity of the water is quite high. Therefore, the large amount of pressure can be bared by this water body. Now, what happens if you are pumping this water out? That means the large pressure that is coming from the top now has to be bared by the soil layers. What happens then? The soil layers start compacting. So the porosity decreases. So what is the mass change inside the control volume because of this compaction? That is another reason to change the mass inside this control volume, right? Then also we can have external effect. We can pump water out, or the water can recharge the groundwater aquifer because of the natural or artificial recharge, right? So this W indicate how much water volume that you pump out or recharge the groundwater aquifer per unit aquifer volume. How much water volume that you pump or recharge the groundwater aquifer per unit aquifer. That is dx, dy, and dz. Right? So that is the W. Then we take the next term. That is this one. What is it? Rate of outflow of mass through the control surfaces. These are the control surfaces. So if I consider only in the Z direction, water can enter from down and water can go out from up. So there are two surfaces, right? So there can be some imbalance between the amount of the water that comes in and the amount of the water that goes out. For example, within a day, the amount of the money that you receive and the amount of the money that you spend can be different, right? So that we can write it like this. So how it is? This is the amount of the water that is going out from this surface. Q is what is coming in, and daba Q over daba Z multiplied by dZ is the variation of the Q with the Z, like this. So this gives you the amount of the water or the mass flow rate through this control surface on the top. And this one gives you the mass flow rate through the control surface at the bottom. So now we are talking only about the Z direction, so that we can write it like this when you simplify it. Then the same equation we can write into the other two directions. We first wrote it in the Z direction. Now we can write it in the Y direction and the X direction. Same set of equations, right? So now this is the net mass flow rate through the control surfaces in the X, Y, and Z direction. That is theoretically should be equal to this one, according to this equation, right? That is this. Now, what is common here? Dx, dy, dz are common, so that we can have a simple equation like this. Then, what is Q here? Q is equal to the flow rate per unit area. From the Darcy equation, we can write it minus K dH over dL. This L can be X, Y, or Z, depend on the direction that you consider, right? So we bring the Darcy equation to this three-dimensional groundwater flow equation. Then we end up with having this final equation. All right. I'm not expecting you to know how to derive this equation, but it is very important you to know how to use this equation. The software like ModFlow. ModFlow is a very famous groundwater flow equation developed by the USGS, United States Geological Survey. All right. So this ModFlow program use this groundwater flow equation. And this is the most general form of the three-dimensional groundwater flow. Why I said most general form? It includes effect of the pumping or recharge. It consider unsteady water flow, daba H over daba T. It becomes zero if you are talking about the steady flow, but this is unsteady, right? For example, the hydraulic head, if it change with the time, we are talking about unsteady flow. And also, you see, we have Kx, Ky, Kz, hydraulic head change in the X, Y, and Z direction. Hydraulic properties like the hydraulic conductivity change in the X, Y, Z direction. So that this equation is applicable for the heterogeneous, anisotropic, unsteady cases. Three-dimensional groundwater flow equation. Okay. So but the point is that you understand this is now a second order partial differential equation. Second order partial differential equation. If you want to solve this equation, you have to apply a numerical method. A numerical program like the ModFlow can solve this equation. But if I ask you to solve this equation during your exam, or if you want to apply it for a simple practical case, it cannot be applied. Therefore, what I'm going to show you now is how to simplify this three-dimensional groundwater flow equation. All right. So I will take a case by case. What it is, the first case is we consider or we assume our aquifer is homogeneous. What is the meaning of the homogeneous? If you say that the aquifer is homogeneous in the x direction, in that case, hydraulic conductivity from this point to this point does not change. Hydraulic conductivity K1 is equal to K2. This is 0.1, this is 0.2. So the hydraulic conductivity does not change along the principal directions. That is the homogeneous aquifer. But still, there are three directions. We said X, Y. So the Kx can be different to Ky, it can be different to Kz. Along the principal directions, the hydraulic conductivity can be different. That is the anisotropic aquifer. This is the anisotropic case. Hydraulic conductivities along the principal directions are different. We call it is isotropic if Kx is equal to Ky is equal to Kz. In that case, it is an isotropic aquifer. Homogeneous mean along the principal direction, hydraulic conductivity is the same. Right? So now you see, if it is a homogeneous aquifer, what we can tell? Along the x direction, hydraulic conductivity does not change. So hydraulic conductivity can be considered as a constant, and you can take it out from the partial differential equation. That is why hydraulic conductivity come here now. It is a constant. This is also constant, right? That is the simplification for the homogeneous aquifer. Then, if you can say the isotropic, in that case, Kx is equal to Ky, which is equal to Kz, which you can write as a common parameter, which is K. Right? That is how you simplify it for the homogeneous and the isotropic case. Then, if you can assume the flow is steady, what it mean by the steady? Hydraulic property like the hydraulic head does not change with the time. So the dA by H over dA by T term is equal to 0 if it is steady. In that case, this part here is become 0. So that steady flow, this part is become 0. That you can write it like this. Now you see how simple the equation become when you apply the assumptions. You can apply the assumptions, but you have to make sure that these assumptions are valid in the practical cases. Right? For example, during the pumping test, in the beginning part of the pumping test, hydraulic head change very rapidly. Drawdown is very significant. Therefore, in that time, you cannot assume the flow is steady. Right? So you have to be careful when you are applying these assumptions. Right? Now, I'm going to solve a couple of examples by using these assumptions. Right? So in the exam, I may give you this three-dimensional groundwater flow equation. As I said, I am not expecting you to know how to derive it, but you should know how to simplify it and use for the given case. So this derivation is important you to know. All right. So what are the assumptions? It is homogeneous, confined aquifer, and it is one-dimensional and steady flow. See the set of assumptions. There are a lot of assumptions. Now this is the three-dimensional general groundwater flow equation. What it says? First thing is that it is one-dimensional. Water flow only in the X or Y or Z direction. Let's say it flow in the X direction alone. In that case, if it is one-dimensional, Y and the Z directional flow you can neglect. So you see now, the equation become very simple. Then what else? It is homogeneous. If it is homogeneous, this K you can take it out, consider it as a constant and you take it out. What else? It says that it is a steady flow, so that the dA by H over dA by T term is also 0. Hydraulic head does not change with the time. And also there are no abstraction, no recharge, so that the W term is also equal to 0. Now it becomes a very simple equation. What is it? This is the equation. Of course, the hydraulic conductivity cannot be 0. Therefore, the dA by squared H over dA by X squared should be equal to 0. Then we do the integration. Since we are talking about the change of the hydraulic head only in the X direction, we don't have to use dA bar. What we can use? We can use D. D squared H over dx squared is now is equal to 0. You can take the integration of this one to find out the equation for the hydraulic head. Right? Integrate one time. How it come? dH over dx become a constant, A. Do the integration one more time. H is equal to AX plus B. Right? Having two boundary conditions will give you the profile of your piezometric head. If it is the confined aquifer, it is the piezometric head. If it is the unconfined aquifer, it is the water table. Somehow, how this piezometric head change along the X direction will be given by this equation. What you need? You need to find A and B. Two boundary conditions will be enough you to find out A and B. All right? In the exam or in the field, you may have different boundary conditions. In this case, for example, probably you know when X is equal to 0, what is the flow rate? You may know it. So that can be considered as an boundary condition. Right? So that apply that boundary condition to this equation here so that you can find out A. I'm not going to solve in detail. I'm sure you can manage it. You know how to do the derivative, how to take the integration, how to substitute the boundary condition and find out the coefficient. That part is easy, simple mathematics, right? So find out A by using this boundary condition. Then to find out B, you need another boundary condition. That can be when X is equal to L, H is equal to HL. For example, let's say X start from here. When X is equal to L, H is equal to HL. Right? So that is your second boundary condition. Substitute it. You have the equation for the variation of the piezometric head with the X. Now, you need to remember what are the assumptions that we made to get this equation. We assume that flow is steady, unidirectional, then homogeneous, no pumping, no abstraction. These are the assumptions we made. Okay. So these are two set of boundary conditions. You don't have to stick only into these boundary conditions. For example, here I have given you another set of boundary conditions. When you do your homework, I need you to use these two boundary conditions and get a similar equation like this. All right. So that is a homework. Right. Now one more case. One-dimensional groundwater flow. In this case, the pumping is not equal to 0. You can have recharge or pumping and it is not equal to 0. That is also possible, right? Okay. So now here we introduce another term called the R. How did we define the W in the original equation? That is the water volume that you pump out for unit aquifer volume. This is the aquifer volume. For this aquifer volume, what is the volume of water that you pump or recharge? But R is defined as the uniform recharge per unit surface area. If you have an aquifer like this, now this is the unit surface area. So what is the water volume that you pump out or you recharge per unit surface area? Therefore, there is a clear relation between the W and R. What it is? W multiplied by the saturated thickness will be equal to R. That is the relation. All right. So now, again, we start applying the assumptions. It is unidirectional, so that this is equal to 0, this one also equal to 0. And it is steady case, so the delta H over delta T term is also equal to 0. Now it becomes like this. Again, very simple equation. Why there is a minus sign here? In groundwater flow, when we have a recharge, we consider it is to the downward, so that it is considered negative. If it is pumping water out, it is considered positive. That is why you have this negative sign here. Right? Now, again, this is a second order equation. You can take the integration one time. So you end up with having this equation with the constant. You need one boundary condition to find out A. We do the integration one more time, another constant comes in. So now you need two boundary conditions, right? So that what you do, you find out this A and B using two boundary conditions, right? So this is a confined aquifer. This is a confined aquifer. Therefore, we need two boundary conditions to find out A and B. So what are these two boundary conditions? So let's say it is a case like this. Here we have an impermeable layer, not only at the bottom, but also at the left-hand side. And here we have a uniform recharge. In addition to that, there is a large lake here. If you have a lake, what happens? This hydraulic head becomes constant at the lake. Therefore, what happens is that we have this uniform recharge coming from the top, so that the water table or the piezometric head actually change like this. This is the lake level, water level in the lake. Because of the uniform recharge, the piezometric head increases like this. But at this point, it is an impermeable layer. So the hydraulic level become horizontal at this point like this, because it is an impermeable layer. There is no water movement beyond this level, right? If there is a water movement, there should be hydraulic gradient, so that the gradient here should be negative. But because there is no water movement, because it is impermeable, hydraulic gradient become horizontal here. So we use these two boundary conditions. When x is equal to 0, if you consider x start from here, when x is equal to 0 at the impermeable layer on the left-hand side, dH over dx, that is the hydraulic gradient, is equal to 0. Why it is? Because it is horizontal. That can be considered as a one boundary condition. What is the second boundary condition? When x is equal to L, that means from here to here, the length is L. Hydraulic head is equal to the head of this lake. That is H equal to capital H. Now you see you have two boundary conditions. Substitute again to the equation and get this equation for the piezometric head. Right? So what I want to say you here is that depend on the given condition, you should be able to simplify the equation. Three-dimensional groundwater flow equation should be able to simplify it based on the given conditions. It can be steady flow, it can be unsteady flow. Then it can be one-dimensional or it can be three-dimensional. Or it can be homogeneous or it can be heterogeneous. So based on the given boundary conditions or based on the given assumptions, you simplify the equation. After that, you come up with the general equation with certain set of constants like A and B. Then you use the given boundary condition, simplify the equation to find out the general equation for the hydraulic head. Right? So that is expected. So you should be able to understand what are the assumptions and what are the boundary conditions, then how you simplify the equation. All right. Now, so far what we discuss is how the hydraulic head change in a confined aquifer. Confined aquifer, what it is? It is an aquifer between two impermeable layers. But what if it is an unconfined aquifer? Can someone tell me what is the major difference between the confined and the unconfined aquifer when it comes to the governing equation? I'm talking about the governing equation. What is the major difference? Anyone? Okay, because of the limited time, I will explain. The major difference here is that you remember this equation. Where is it? Yeah. When we talk about the confined aquifer, the saturated thickness is constant. That is B. Confined aquifer is an aquifer in between two impermeable layers. So this is the first impermeable layer. This is the second impermeable layer. So this saturated thickness is constant. But when it comes to the unconfined aquifer, this saturated thickness from here to here change. Why it is? Because that saturated thickness is the thickness of the water table or the height of the water table. Water table height change with the water flow. Why it is? Because of the head loss. Hydraulic head decreases in the direction of the water flow. So the higher head here and lower head here along the direction of the water flow. Therefore, the major difference between the confined and the unconfined aquifer is that this saturated thickness, H change, it is a variable. We cannot consider it as a constant. That is the major difference between the confined and the unconfined aquifer. All right. So again, when we talk about the simplification of the equation, we make certain assumption for the unconfined aquifers as well. That assumption, a set of assumptions were first introduced by Depute. So we call them the Depute assumption. So the first assumption is curvature of the free surface is very small so that the streamline can be assumed to be horizontal at all sections. When you have a hydraulic gradient like this, water flow is not entirely horizontal. It has a gradient like this. So it has a horizontal component and a vertical component. But depute assumption asks us to consider that this curvature of the free surface is very small. This curvature is very small, so that we can consider the water flow is only in the horizontal direction. The second assumption is hydraulic grade line is equal to the free surface slope and it does not vary with the depth. Remember, we talk about the hydraulic grade line in pipe flow. In other words, here the hydraulic grade line is the grade line of the piezometric surface. So when it comes to the unconfined aquifer, that grade line slope is equal to the slope of the free surface. In that case, we can consider this water flow is horizontal, right? So that is an assumption we made. In that case, we can write Q is equal to AV. Then if you consider a unit aquifer width of this aquifer is 1 unit. So this is 1 meter. In that case, we can write simple Q. So the relationship between capital Q and simple Q is that we are talking about 1 meter unit width. So Q is equal to area is now what? H multiplied by 1 meter. H. This is the H multiplied by 1 meter. That is the area multiplied by the sea velocity. That is K dH over dx. And you know that we bring minus sign here for the Darcy equation. Right? So this is the equation for the unconfined aquifer. Again, you can take the integration one time so that the equation become like this. So apply one boundary condition. For example, when x is equal to 0, if you know what is the water level, then you can have the equation for the variation of the water level in the x direction, right? So this is the equation. So you should be able to come up with this kind of an expression for the water level variation based on the given condition. It can be a confined aquifer or it can be an unconfined aquifer. All right. So you should be able to derive it. Now, I think we are almost near to the end of the class, but still there are, I think, a couple of cases I would like to discuss, but we don't have the time. So I will discuss these cases in next class. Do you have any questions so far? Any questions? Lakmali, any question? So at least, can someone tell me whether you understood it or not? Yes, we have a message. Presentation slides. Yeah, okay, I will upload them on, I will send it to the instructor so that she will upload it. Please, if you are communicating, communicate with the instructor so that she will send me the messages. Normally, I keep my communication with the instructor. Okay. Right. I will do that. I will upload the, I will send her the PowerPoint presentation. Anything else? Right. No, okay. If there are no any other questions, I will stop now. The rest of the things I will ask you to study but I will go through them very quickly in the next class. And also I have given you, I don't know whether it is a tutorial or the assignment, how it works with you. But anyway, I have given this set of questions to the instructor. She will communicate with you. So I need you to work on those examples so that this kind of simple applications will be clear to you. All right. Okay, then that's all. Thank you very much.
Thank you, sir.